Every single year, Edexcel always ask a rigid bodies question, which in other words is just like a moments question where they give you like a ladder or some kind of beam or rod. So usually you get some kind of thin ladder that's leaning against a wall. Could also be like this one where the ladder, or in this case the ramp, is leaning against like some kind of circle. Like this one where you've got like the plank here, but there's like a string that's holding the plank up and the plank is leaning against this rough wall, in this case, yeah, rough vertical wall. So as I literally said at the start of this video, you're always going to do moments of these questions. So the first step is always to take moments about the position where there's friction. So again, with this question here, there is friction at A, so rough vertical wall. This wall is rough, okay, so there's friction on this wall. So you always take moments about the position where there is friction acting on the ladder. So point A, you take moments about point A. Exactly the same with this one. So in this case, the ground is rough, so there's friction on the ground. The wall is smooth, the ground is rough. We take moments about A, because A is the point where there's friction and the rod is contacting the friction. Now you may be wondering, what if both surfaces are rough? Well, what you'd have to do, you'd have to do moments on both A and B and do like simultaneous equations if that was the case. I've not seen a past paper question like that, but maybe this is the year. Now with these questions, the rods are going to be in equilibrium, so that means that the anti-clockwise moments are the same as the clockwise moments. So you resolve the moments, make them equal to each other. Now in this case, do you notice how the rod is in limiting equilibrium? So remember, limiting equilibrium just means that it's about to slide. So in other words, friction is equal to mu times r. Because remember, friction is less than or equal to mu times r, but if it's in limiting equilibrium, it must be equal to mu times r. I did a video ages ago explaining why it's less than or equal to mu times r, not always equal to mu times r. So just search in my videos, just type into the search engine A-level Maths Tutor UK friction, you'll probably see that video. So that comes in handy, for example, this part A of this question here, right? So show that mu is greater than or equal to half cot theta. Of course, when a rod or a plank or a ladder is in equilibrium, it's not only true, not just true that the anti-clockwise moments equal the clockwise moments, it's also true that if you add up the forces going upwards, they must be the same as the forces going downwards, right? So resolving forces vertically. Also, the forces going to the right must be equal to the forces going to the left. Again, resolving forces horizontally. As an example, if we think about the weight of this beam, so the weight is located in the center of mass. The weight's going down. Yeah, that's the force going down. That weight must be equal to the normal reaction force A going up. So that reaction force is equal to the weight in the middle going down. There are no friction forces on the wall here because the question says that the wall is smooth, so there's no friction on the wall. It's just the weight is equal to reaction A. Normal reaction A, normal, that's very important. And also if we resolve the forces horizontally, so the normal reaction force at B, so remember, normal reaction forces are always perpendicular to your surface, so the normal reaction force at B is going straight to the left. That must be equal to forces going to the right, so in this case the friction going to the right. So the friction must be going to the right because obviously it wouldn't be in equilibrium if it was not going to the right. Again, your first step is always going to be to take moments about the friction point, take moments about A, then you're going to resolve your moments, so clockwise equals anti-clockwise, and then what you're going to be able to get is you're going to be able to get this reaction force, this normal reaction force at B, okay? So you're going to be able to get that normal reaction force at B, so it's going to be half A times by the perpendicular component of the weight is equal to 2A times by the perpendicular component of the reaction force at B, and then you can resolve that reaction force at B, and then you can realize, well, actually the friction going to the right is equal to the normal reaction force going to the left at B, and then you're going to be able to get this inequality there because friction is less than or equal to mu times r. So that's kind of how you go about this part A. So if we go back to this question actually with the circular surface, so the normal reaction force at C is going to be perpendicular to this beam A to B, yeah? So it's going to be normal reaction force perpendicular. Even though the questions may look different in the past papers, the strategy really is always the same. Step 1, take moments about the friction point. Step 2, resolve the forces vertically or horizontally, and then basically you're going to be able to answer all these questions here depending on the situation. Now, if you actually want me to do one of these past paper questions, comment below yes, I will pick the hardest one and I'll go through the past paper question and show you the method.